In this video on thermochemistry, we're going to do some calculations using stoichiometry to calculate the enthalpy of a specific situation for a reaction. So when you're using stoichiometry, the enthalpy values have been experimentally determined, and the enthalpy values that you get are based on stoichiometric ratios here. So let's talk about a reaction. We have the reaction for the combustion of methane. So if you look here, we have methane plus 2 oxygens gives you carbon dioxide and 2 waters. And we're giving you the enthalpy value. The enthalpy value is negative 890 kilojoules. So what does that mean? Well, that first tells us that this is an exothermic reaction, which makes sense because, well, it's combustion of methane. So burning natural gas, that gives us fire. So the units are really important here, and the one thing I want to talk about real quick is the unit of the methane, of the enthalpy that will give people some difficulty, and it's this mole part. The unit says kilojoules per mole, and that is saying if you use a mole of reaction that's balanced, so this would be considered a mole of reaction, then you would get 890 kilojoules of heat released. So keep that in mind. That's where that unit comes from. It's the balanced equation. And if you are talking about the stoichiometric ratios, that's the enthalpy or the heat that is either produced or released or absorbed when the reaction goes. So if we used 1 mole of methane and 2 moles of oxygen, then we will get exactly 890 kilojoules of heat released. We can also write the reaction putting the enthalpy into the reaction. This is called a balanced thermochemical or thermodynamic equation. And because this is exothermic, notice that we put the enthalpy as a product. If it was endothermic, we would have put it over here on the reactant side. So this shows us that these stoichiometric relationships will produce that amount of heat. So sometimes where we have a different stoichiometry going on, we're not going to use 1 mole of methane and 2 moles of oxygen to produce 1 mole of carbon dioxide, 2 moles of water. They're going to change things up, and they're going to give us different amounts of the methanes or the oxygen and ask us, well, how much heat is released if I do it this way? So here's an example. Given the reaction above, how much heat is released when we use 8.2 grams of methane instead of 1 mole. So this, just treat it just like a normal stoichiometry problem. So we're going to start with 8.2 grams of CH4. And what's the first thing you always do when you're given a mass? Change your mass into mole. And so for methane, there are 16 grams in 1 mole of methane. And then we're going to use our stoichiometric ratios to figure out how much heat is going to be produced. And for 1 mole of methane, we would produce negative 890 kilojoules of heat. And so we do that calculation, and we get negative 460 kilojoules of heat. Or we could say 460 kilojoules of heat are released. The sign and the meaning of the statement, they go hand in hand. Another example, same reaction. This time we're going to use 12.3 grams of oxygen. And the question again is, how much heat is released? So again, we're starting in grams. We're going to go to moles. there are 32 grams in a mole of oxygen. And here's a really important thing to pay attention to. For every 2 moles of oxygen, I get negative 890 kilojoules. Why is it 2 right here? Well, it's because the stoichiometric ratio in the reaction is 2 moles. 2 moles of oxygen would give you 890 kilojoules. And so we need to keep that ratio together. So this is the molar ratio straight from the reaction. We do that calculation and we get negative 171 kilojoules of heat, or 171 kilojoules of heat released. Watch your stoichiometry. That's really, really important. And whenever you are using a molar ratio with the enthalpy in it, make sure that you are checking this to match the coefficients from the reaction. Okay, practice problem. We have nitrogen monoxide reacting with oxygen to make nitrogen dioxide, and we're telling you that the enthalpy is negative 112. Also keep in mind, this means it's exothermic. So we could also write the reaction as 2NO plus O2 gives us 2NO2 plus 112 kilojoules. Written both ways, you'll see it presented to you both ways. All right, we are starting with 53 grams of nitrogen monoxide, 42 grams of oxygen. How much heat will be produced? Well, the first problem is, this is a limiting reaction problem. So we're going to have to figure out which one is the limiting reactant, and that's going to be the one that's going to determine the heat. All right, so it's going to be the one that's going to produce the least amount of heat. So let's start with the 35 grams of nitrogen monoxide. Again, turn grams into moles, and it is 30.01 grams in a mole of nitrogen monoxide. And for every 2 moles of NO, we end up getting negative 112 kilojoules of heat. Calculate that out, negative 65.3 kilojoules. Do the same thing, but with the other reactant, the oxygen. 42 grams of oxygen. There are 32 grams of oxygen in a mole of oxygen. And now we're going to do our stoichiometry. And for every 1 mole of oxygen, we get 112 kilojoules. Do the calculation, that would give us negative 147 kilojoules. So which one's going to produce the amount of heat? Well, the limiting reactant is going to be the one that's going to produce the least amount of heat. And so that would end up being the nitrogen monoxide. That's the limiting reactant, and that's going to tell us how much it's going to heat, how much heat it's going to produce, and we would produce 65.3 kilojoules of heat. Do the calculation and figure out which one's going to do the amount of heat. So pay attention to your molar ratios. Coefficients matter when you're doing a stoichiometry problem. And I hope that helped. And there's our calculations. So ultimately, what are we going to find? We're going to find the limiting reactant, and then it's going to be the one that produces the least amount of heat. There's lots of ways you can go about doing this. You could find the limiting reactant first and then do the enthalpy calculation. It doesn't matter as long as you